Greetings to Dr. Rizwan. My name is Colette Fan, and in this video, I'm going to demonstrate about my individual assignments about the digital voltmeter that can measure from 0 volt to 9.9 volt. So let's see how we can do this. First, let us check our code here. So here is the main code of the system. I'm going to explain one by one. First we have our register definition here. So in this code, it start with define the memory address for the RCC and the GPIO-B and GPIO-A, and also the ADC, because we're going to use analog digital converter later on, so we have to define it first. Since it is a bare method code, so we have to do all of this. We have to define the register first so that the software can know which hardware peripheral have to use. And then move down here. Here is our function prototypes. There's all the function that we have created for this project. First, this one is the delay function. It will use in the display. Okay, so here is the important function, the hardware initial function. So in this hardware initial function, it will enable the internal clock for port A and then port B and also the ADC1 modules. It will set the pin PA0 to analog mode for sensing. So yeah, here you can see that tree is inserted to set the PA0 into analog mode. So we have to do this, and later on the port B pin is set as digital output so that it can drive the display segment and our indicators LEDs. Let's see here. First we must kill the port B first, and then we set it to the mode that we want. Okay, so next let's look at the ADC read function. So in this function, the ADC read this function will trigger the conversion process by setting the SWSTART. The full name is software start. Once it is triggered, it will start convert the voltage on PA0 into a digital number by setting the SW software start bit, and then we wait for the end of conversion flag, which is the EOC flag in the status register. So here is it. We use this while loop to detect whether the EOC flag is 1 or not. If it is not 1, it stays in this loop, and once the flag is set to be 1, the loop will be break, and then it will return the result in 12-bit value. So 12-bit is 0 to 4095. Yeah. Then here is the control LEDs. We will talk about it later. Now here is our main function. So first of all, the most important thing is to initiate the hardware. We have to initiate the settings so that the port can work as we want. And then we also define two variables here: unsigned integer v total, and then unsigned integer d1, d2, and d3. And okay, so And then in the while loop, we will first get the reading. So in order to get the reading, we need to use our ADC read function, and it will return the value into the low. The low is the 12-bit value, and then for the 12-bit value, it will be scaled to a voltage value through this function. Okay, it will be scaled to the 12-bit. It will be scaled to the voltage value. For example, if our low value is 4095, it will multiply with 100 and then divide by 4096. So as a result, you will get something like 9.999 something. So that will be used for further processing to get the display. Okay, and then okay, here in this loop, we are going to display. Oh, also one thing more, the control LEDs. This function is to evaluate the value of the V total. If the V total is greater than 50, that means the voltage is greater than 5 volt. The green LED will light up, and if it is lower than 5 volt, the red LED will light up. So it can act as the indicator to show what is the range of the voltage right now. Okay, so this is the most important part for the output interface. We divide the V total into three digits, D1, D2, and D3. We break down the V total into 3 individual digits, and then we use a multiplexing loop here. We use a multiplexing loop to we use the multiplexing loop so that it can cycle through the communicator pins, which is pin 12, pin 13, and then pin B14. Okay, so it will display the whole circuit. For example, just now the result we got, V total is 99.9 something, 99.999 something, and after it undergoes D1, it will become 0, right? Okay, so the first digit will show 0, and then move to here. We pull out the PB12. So we select this digit to display the number 0. So where the number 0 come from? It comes from this array segment map D1. This is the array that we define here. Okay, so we predefined it so we can use it. 0 as 3F represents 0, 1, 2, 3, 4, 5 until 9. Okay. So after we getting D1, we have to get our D2. D2 need to be divided by 10 and then moved by 10. So for example, 99.99 would divide by 10 will get 99. Actually there is no fractional point because it is integer, so it should be 99. 99 divided by 10, it will become 9. Okay, it will become 9, and then we find the remainder, we move it by 10. So 9 divided by 10, the remainder will be 9. So that's how we extract the digit out. So the digit 2 will become 9. And then we display. So in order to display, we have to select PP for PP13. So we put out the PP13, we set it to 0, and then we display it using the segment map, the D2 9, because D2 represents 9, so in this segment map it will select the 9, the 9 number, so it's here. Okay, that's how we work. And then also we have to add this 0s at 0, because this represents the decimal point. We want the decimal point to light up on this digit also, so that's why we use this function. And then about D3 we just directly divide by module multiply by 10. So 99 multiplied by 10 will also get 9. So that's how we get our D3. And also notice here that is the delay function after every time we display the number. This delay function is very important because it will ensure the digit appear steady and clear to our human eyes. The microcontroller cannot the 77 cannot display this 3 digit in one time due to the limited pin. Okay, so we have to use the multiplexing loop, so the microcontroller will keep scanning and displaying. So our human eyes can see 3 digits, but actually the microcontroller is displaying one by one. But it also comes with another problem because the speed of the microcontroller scanning is too fast, and our eyes will see the ghosting effect. For example, it should display 1 as the first digit, but after it chooses the first digit, the number of the third digit will come out, so it will produce the ghosting effect. That is not the scenario that we want. So in order to avoid this, we must use the delay function to slow down the speed so that the number can be captured by our human eyes. So that's for the code, and let us move to the simulation part. Okay, now I already opened the physical circuit in the Proteus. So as you can see, the main part, we have our microcontroller STM32F401. So this controller will act as the brain for this digital voltmeter system. Okay, and then we move to here. You can see that the physical connection of the input side. For the input side, we use a 10 volt. I use a 10 volt battery source, and it is connected to a potentiometer, and then a voltage divider network that constructed by the R1 and then R2 and the xenon diode and the capacitor. This hardware configuration can safely scale the 10 volt signal down to a range that compatible with the microcontroller 3.3 volt logic. Other than that, if it is more than 3.3 or 5 volt, if we send the 10 volt directly into the microcontroller will damage or explode something. Okay, so the xenon diode here is placed parallel with the output to provide the to provide a protection, and then the capacitor will ensure the signal smoothing before it enter the analog pin here, PA0. Okay, and then let us look at the output interface here, the 7-segment BCD. The microcontroller is wired to this 7-segment display through the current limiting resistor RN1, and then by using the pin PB0 to PB7, it can controlling the individual segment of the 7-segment display. And then the PB12, PB13, and PB14 is used as a commutator selector for digit multiplexing. And don't forget the PB8 and PB9 that control the red and green LEDs here. It's just simply connection. We connect and then use a 220 ohms resistor to limit the current. So as you see as this, the cathode go to the ground, so it can light out successfully. Okay, now let us start the simulation. 1, 2, 3, go. Okay, as you can see here, the 7-segment display will showing 0.0 watt, and then the red color LEDs is light up. That is because our potentiometer here, the wiper is placed at 1% top, so that means the voltage that going through is 0 watt because it's connected directly to the ground here. So there is no voltage passing through. And then let us see what if I move the wiper 1% down. Okay, 99%. You can see here the 7-segment display 0.1 watt. Okay, and then I do it again. I move down 1%. So you can clearly see here there is a 0.1 voltage increase every 1% of the wiper potential move down. Okay, and I just go faster then. And then yeah, the last percent, it will not increase until 10.0, because as the question mentioned, we only want the range from 0 to 9.9 volts. So in the code here, the maximum number of the law is 4095. If we divide by 4096, it will never reach the 10 volt. Okay, understand? So if we want it to reach the 10 volt, we just divide it by 4095, so that you will get a full voltmeter rating. Okay, and then also notice here the green light lights up because of our control LED function. If the voltmeter is lower than 5 volt, the red LED will light up. But once it equal or greater than 5 volt, the green LED will turn on and the red LED turn off now. Okay, so that is the simulation. Also the reference here. The voltage reference here is very important because we have to ensure we give the 3.3 volt V reference so that it will uh, so that it can divide the raw divide the analog voltage based on our calculation. If we give the reference 5 volt, the whole the logic will collapse. Okay, so that's a successful simulation, I could say, and that's all for the video. Thank you for listening.